Okay, so for those who just started watching the recording, I apologize, I started recording late, but everything so far is review. So last time we did what, how, and how many eigenvalues and eigenvectors there are. And this time we're going to talk about why this is useful. And the point is it gives an answer to this question, what is the best basis in which to represent a linear transformation? Now, before I do that, so this is going to be divided into 3 topics. So one is similarity of matrices. The second is diagonalization. And the third topic is applications of diagonalization. Okay, so let me begin with similarity of matrices. Any questions about this? Is just a review of the last lecture. Okay, so similarity. So before I tell you what similarity is, let me ask you sort of a warm-up question. If A is row equivalent to some matrix R, do A and R have the same eigenvalues? So far, row reduction has been this very nice process that preserves solutions of linear systems, preserves a bunch of other properties. Does it preserve eigenvalues? You can enter what your opinion is in the chat. Some people are saying yes, some people are saying no. It's not totally clear. You have to think about, think about the examples you know. Majority view seems to be no. Somebody said, I hope so. Yeah, that would have been nice, but the answer is no. Can somebody give me an example of 2 matrices that are row equivalent but don't have the same eigenvalues? So by the way, the reason it doesn't just a priori is that this equation is not a linear system, right? Ax equals lambda x is not a linear system. So raw operations don't have to preserve the solutions. But can anybody think of an example? Great, somebody gave a very simple example. Consider the matrix 2, 2. This has eigenvalues just 2. And this can be row reduced. The row echelon form is 1, 1. And this has eigenvalues 1. So no way, actually, right? Any invertible matrix is row equivalent to the identity. But certainly the eigenvalues don't have to be 1, right? So not at all. So what we're going to discuss now is an operation on matrices which does preserve the eigenvalues. Any questions about this question and answer, by the way? This is important to understand. Okay. Somebody raised a very interesting speculation in the chat. I encourage you to think about that. But now I'm going to tell you an operation that does preserve eigenvalues. So here's the definition. Or actually, I'll do it on the next page so I can keep everything together. A matrix A, n by n, is similar to C, which is another n by n, if P inverse AP equals C for some invertible matrix P. Okay, so similarity is this relationship. Now, this might look a little weird, right? So this is saying that if you multiply on the right by P, multiply on the left by P inverse, you get C. And I should say that this is equivalent. You can rearrange this, right? Equivalently, A equals PCP inverse. Why is that equivalent? Anybody tell me why?
Can't you just do P and P inverse of both sides and then?
Yeah, multiply on the left by P, that cancels the P inverse, and multiply on the right by P inverse, that cancels the P. So you can write this equation in a couple of different ways. It's also equivalent to, sometimes you, yeah, okay, I'll just write it this way. Okay, so that's the definition of similarity. Now, observe that this definition is symmetric in the sense that if A is similar to C, then C is similar to A. Why is that? So C is similar to A would be that there's some matrix Q so that Q inverse CQ equals A.
You can just set Q equal to P inverse.
Exactly. And the reason is, this is P inverse A, P equals C. And then the relation between these things is you just said Q equal to P inverse. Right. So, okay. So it's a similarity is a symmetric notion. And what is the meaning of this? Well, let's think about it. It just looks like a funny algebraic thing right now, but it actually has a very nice meaning. Well, I have my matrix A. So now it's an n by n matrix. So that's a linear transformation from Rn to Rn, right? So let TA be the linear transformation from Rn to Rn, which takes x to AX. Okay, so TA is just multiplication by A. And now I also have here this invertible matrix P, right? So now I'm going to interpret this P in a very specific way. I'm going to call its columns B1 through Bn. And I know P is invertible, right? So what can I say about the columns B1 through Bn as vectors?
They're linearly independent.
They're linearly independent. What else can you say?
We can say that they span Rn.
Yeah, they're linearly independent and they span Rn. So that means that they're a basis, right? That's the invertible matrix theorem. But now, let's think about, the last week we did change of coordinates, right? So if this is a basis, if B1 through Bn is a basis, then we can interpret P as a change of coordinates matrix. Now, it's a change of coordinates matrix between what two bases?
The standard basis in B.
The standard basis in B, right? It takes a vector, it takes B coordinates and turns them into standard basis coordinates. Any questions so far? I'm just interpreting my P in a particular way. Oh yeah, and I'm interpreting my A in a particular way too. A is just the matrix of TA with respect to the standard basis. That's something we did before the first midterm, right? Any questions about this? This is just the setup. I haven't told you what I'm going to do with it yet.
Could you explain why it's from B to E, please?
Sure. I mean, just because, the columns of P are just the basis vectors of the B basis written in the E basis, right? So if you just write down a vector, that's the same as writing it in its coordinates in the E basis. So what I'm saying is that this is the same as this. Does that answer the question?
Yeah, thank you.
Yeah. And oh yeah, I should just say E is the standard basis. Okay, so now with this new interpretation, I can interpret the similarity equation up here. I can rewrite it, right? What does it say? Well, P inverse is the inverse of this change of coordinates matrix, which is another change of coordinates matrix. What is P inverse going to be?
B to E.
E to B. Yeah, the arrow is going to be reversed, right?
Yeah, sorry.
So this is going to be P E to B inverse times the matrix of TA in the E basis times the matrix times the change of coordinates matrix from B to E. And as we discussed in the last lecture, this inverse just reverses the arrows, right? So this is just going to become E to B. And so the equation says that this equals C, right? That's the same equation, just interpreted in this way. But now the left-hand side, what is the left-hand side? We learned about change of coordinates for linear transformations last time. What is the left-hand side?
TA B to B.
Yeah, exactly. It's just the matrix of T of TA in the B basis, right? So this implies that the matrix of A in the B basis is equal to C. Okay, and this is the meaning. So similarity means, the meaning of similarity is that if C is similar to A, then C is the matrix of TA in some basis. So let me summarize this. C is the matrix of TA in another basis. And so that means similar matrices represent the same linear transformation in different bases. Okay, so that's the meaning of similarity. This equation actually has a nice meaning. It's just saying that C represents the same linear transformation in a different basis, and that different basis is given by the columns of this P. So any questions about the definition of similarity?
This is not necessarily about the definition, but can you explain the notation for BTAB?
Yeah. So this notation is the same notation that we used, I guess, last week, and this is matrix of TA relative to B and B as the input and output bases.
So the right subscript would be the input, the domain, and then the left subscript.
Exactly, and they're both B.
Okay, yeah.
So see, in this equation down here, the subscripts line up perfectly, right? That's why this is a kind of a good notation. And that's how you get the B to B. You go B to E, and then you have the matrix of A and the E to E bases, and then you go from E to B. So
Got it. Thank you.
yeah, so it might help to draw a picture or a diagram of this. Sometimes it helps. If diagrams don't help you, you can ignore them. The diagram is that the original matrix A was a linear transformation from Rn to Rn. And what I've done here is, I've written it in a different basis. So, or actually, I'll just write the matrices. So A was originally, multiplication by A was up here. Multiplication by C is down here. And the way they're related is like this. So this is a special case of what we were doing last week, and that's the way to interpret what this equation means, similarity.
Are we always going to be starting in the standard basis, or are we going to find similarities between two matrices, like in different bases?
Well, so similarity is an algebraic condition, right? It's just a statement about matrices, which are just arrays of numbers. So it's just this equation. What's written here is the interpretation of this equation. So what this is saying is, if you interpret A as the matrix of TA in the standard basis, then what's written here is correct. But you could interpret A as the matrix of some other linear transformation in some other basis.
Okay, cool.
I'm not going to do that right now because it's just makes things more complicated. But you could do that. Really, what I'm doing here is I've decided to interpret A as the matrix of TA in the standard basis. But I could interpret A as, I could interpret P and A as some different, change of coordinates matrix and different matrix of some linear transformation, and this would mean something else. But if you interpret it this way, this is what it means. Okay, so that's similarity. Now, what's good about similarity in our present context? Well, it preserves eigenvalues and eigenvectors. Preserves eigenvalues and does something very predictable to eigenvectors. So let me write that now. So here's a theorem. If A is similar to C, then they have the same eigenvalues. With the same algebraic, or let's say geometric, same geometric and algebraic multiplicities. Okay, so similarity preserves eigenvalues, unlike row reduction. Any questions about the statement? Okay, let me tell you the proof. So let's prove the same eigenvalue statement first. Well, let's suppose X is an eigenvector, or let's suppose lambda is an lambda is an eigenvalue of C if and only if Cx equals lambda x for some x equals 0, x not equal to 0, right? That's the definition. But now let's look at the similarity equation, right? P inverse AP equals C. So this is true if and only if P inverse APX equals lambda x for some x. And now I want to conclude that lambda must be an eigenvalue of A. Can anybody think about how to reach a statement that tells me something about the eigenvalues of A?
The polynomial.
You could do that, but from this statement,
Okay.
can you think of something to do to this last equation that would tell me something about the eigenvalues of A? Yeah, P and P inverse cancel to identity, exactly, right? That's the definition. So remember out here that the inverse has this property, right? So what would I do? No, they don't cancel. Sorry, they don't cancel like this because there's an A in the middle. Sorry. So P times P inverse is identity. P inverse AP is not identity, right? The order really matters. So that's not the answer.
So like you multiply P and P inverse like on left and right, but like on the right of this equation, you will have the identity matrix.
Yeah, that doesn't quite make sense, right? You can't multiply the right-hand side. The right-hand side is just a vector. So you can't multiply it on the right by a matrix. That doesn't make sense.
Oh, yeah.
Something even simpler than that.
Augmentation.
No, just think about it algebraically.
Could you subtract lambda x?
You could do that, but that I don't think that'll get you. So you want to eventually get to a point where you have a y equals lambda y for some y. It doesn't have to be the same x. That's maybe the hint.
Can you divide by x?
No, x is a vector. You can't divide by a vector.
Do you left multiply by p?
Yeah, just multiply by p. And because p is invertible, this is if and only if, right? When you multiply a vector by an invertible matrix, you can unmultiply by multiplying by the inverse. If you multiply by p inverse on both sides, what do you get? Well, you get p inverse a px equals lambda px. But p inverse is identity, right? So apx equals lambda px. But now I'm done, right? Because px is an eigenvector. And why is px not equal to 0?
We said that x isn't equal to 0 and p is invertible. So
exactly, because p is invertible. But this is great, right? Because now px is an eigenvector of C. So we actually just proved, so this is if and only if lambda is an eigenvalue of A with eigenvector px. So maybe let's make this better. Lambda is an eigenvalue of C with eigenvector x, if and only if. So now let me erase these. If and only if these equations are true, right? So this is a nice little calculation. It tells me that the eigenvalues are preserved and the eigenvectors are not preserved, but they just get multiplied by p. Right? So if x is an or depending on which direction they're going, if x is an eigenvector of C, then px is an eigenvector of A. So that's why they have the same eigenvalues. What about the same geometric multiplicities? So let me write that in mathematical notation. So dimension of eigenspace of lambda. Well, okay. I don't have a good notation for this, so let's just write it out. So the dimension of the null space of A minus lambda I is equal to the dimension of the null space of C minus lambda I. Well, we kind of proved it up there, right? We have that X is in the null space of C minus lambda I, if and only if Px is in the null space of A minus lambda I. We just proved that. That's literally what's written up above, right? So, well, you can check that this, this implies that P is actually an isomorphism between the null spaces. And so they have the same dimensions. And the dimensions have to be equal. If you don't like this language of isomorphism, just again, think about it more concretely. Dimension means the size of a basis, right? So if you have a basis for null space of C minus lambda I, you can just multiply it by P and you'll get a basis for null space of A minus lambda I. So they have the same, so we just finished the proof that they have the same eigenvalues, the same geometric multiplicity. Any questions about these? So this first statement is from what we did above. So again, similar means P inverse A, P equals C. Somebody asked if it's okay to say that they have the same eigenvalues but proportional eigenvectors. I wouldn't use the word proportional because proportional usually means like scalar multiple. But it is true that they're nicely related according to this P. Okay. So now let me do algebraic multiplicity. So we'll actually prove that they have the same characteristic polynomial. And that will in particular imply that they have the same algebraic multiplicity, because algebraic multiplicity is the number of times an eigenvalue appears as a factor of the characteristic polynomial. Well, what's the characteristic polynomial of C? That's the determinant of C minus lambda or Ti. I'm using the variable T, right? But now the similarity equation tells me this is equal to the determinant of, P inverse AP minus T. And now I'm going to do something sneaky. I'm going to write the identity as P inverse identity P. I can do that, right? P inverse identity P is just P inverse P, which is identity. Any questions so far? Okay, I'm
I had
running
a
out.
question.
Yes, please.
Sorry. Why do you have to multiply P by P inverse if that's equal to the identity matrix?
You mean in the last thing I wrote?
No, I was wondering like in general, like why do you multiply P inverse times P if that, because isn't it that like if you multiply, like you said it on the side too, like P times P inverse equals I. So then what's the purpose of putting P inverse in P?
In the last step, you mean?
Yeah.
Yeah. So it's kind of a sneaky trick. You'll see in a moment. It looks like there shouldn't be any purpose, but let's continue on the next page. So the expression was characteristic polynomial of C with respect to T is now equal to determinant of P inverse AP minus P inverse IP times T, right? So now I'm going to do something which is just matrix algebra. Can you factor anything out of this? I've written it this way to be very suggestive.
P inverse
You can factor out P inverse
and P.
and P. This is P inverse A minus D times identity times P. That's why I threw in the P inverse P. Okay, but now I'm going to use properties of determinants. This is equal to determinant of P inverse times determinant of A minus D identity times determinant of P. But determinant of P inverse is equal to what?
1 over determinant of P.
Yeah, 1 over determinant of P. And the thing in the middle is a characteristic polynomial of A. And this is not 0, so cancel, cancel. No, not 0. You just cancel. They cancel with each other. And that's it. That's the proof. Okay, so similarity is perfect for preserving the characteristic polynomial, right? If you only did this on one side, you wouldn't be able to pull off this trick because you wouldn't be able to introduce this P inverse P. In all of these cases, you will see that you need P inverse and P on exactly this way on both sides to pull this off. So that's the proof of why similarity preserves these properties. Any questions? So summary is similarity preserves, these properties. So that's similarity. And so row reduction doesn't preserve eigenvalues. Similarity preserves eigenvalues and multiplicities and the characteristic polynomial. Okay, well, what is the point of that? So that brings me to diagonalization. So remember, we asked this question, what is the best basis in which to write a linear transformation? And I will tell you the answer. The answer is in a basis of eigenvectors. If it exists. So we don't know that there's always a basis of eigenvectors. But from the first slide, we saw that under some sufficient conditions, S1 and S2, you have n linearly independent eigenvectors, and then they have to be a basis, right? By the Goldilocks theorem. So now so this brings us to diagonalization. So let me define what diagonalizability is. So a matrix is a matrix A, let's say, or n by n matrix is diagonalizable if it is similar to a diagonal matrix. So what does that mean? It means P inverse AP is equal to D for some diagonal D. Diagonal means only the diagonal entries are not 0. And this, by the, we thought about what the interpretation of similarity is here, right? A is similar to C if C is the matrix of A, of the multiplication by A in some other basis, right? C is the multiplication of TA in another basis. So it's equivalent to saying that the matrix of multiplication by A in some basis is diagonal. Okay. Sorry, the word after linear is trans, so let's just write transformation. So that's the definition of diagonalizable. And it's going to turn out that this magic basis that makes multiplication by a diagonal is the basis of eigenvectors when it exists. Now, why is this good? Well, okay, maybe before telling you why it's good, let me just, or why is this the best basis? Well, it's desirable because, you know, if you have a diagonal matrix, let's say this matrix, and you multiply it by a vector, well, you don't need to know linear algebra at all to know what it does. It just acts on each coordinate separately. Right? So diagonal matrices act separately on the coordinates. So in particular, there's no interaction, right? If I wanted to compute this function, like let's say this matrix is D. If I wanted to compute dx, there's no interaction between the coordinates. So there's no interaction.
Professor, I have
Yes.
one question. So, are these different from upper triangular, as in the upper have to be also zeros?
Yeah, they're very different because this has to be 0, this has to be 0. Diagonal matrix means, yeah, so maybe I should say a diagonal matrix is a matrix which just has, you know, only AII are non-zero. Or maybe D, sorry. Only diagonal entries are non-zero.
Can one of them be 0?
Yeah, many of them could be 0. Okay, maybe a better definition is all the, so A, okay. It means D is diagonal, means that Dij is 0 when I not equal to j. Yeah. So this is an example of a diagonal matrix down below. Okay, so that's a diagonalizable matrix. And those are the simplest matrices. Like anybody who uses linear algebra will tell you that given a choice, the easiest matrices to understand are diagonal matrices because you don't even need to know linear algebra. It's just doing something separately to each entry. It's just something to do with numbers. Okay, so let me now tell you an important theorem, which is not hard to prove. Well, okay. I could either do another theorem or show you an example of the application of the theorem. Anybody have a preference? Do you want to do the theorem or the example first?
The example.
Okay, yeah. So this has been a somewhat light on example. So let's do an example and then I'll tell you the theorem which generalizes this. So the example is just the matrix from last time. Okay, so as a linear transformation, it's not so clear how to understand what this does, right? So if you multiply this by x1, x2, x3, then what do you get? Well, you know, you get x1 plus 3x2 plus 3x3. Sorry, I don't know what. Yeah. And then, you get minus 3x1, minus 5x2, minus 3x3, So the coordinates interact, right? Now, it would be nice if we could, if we could find a similarity that turns this into a diagonal matrix, because then, well, I'll show you a concrete application later. That would be much simpler to understand. Okay, so I'm gonna find a matrix, find a diagonal matrix that's similar to this matrix. So it's gonna involve two steps. So step one is to compute eigenvalues and eigenvectors. So we did that last time. The characteristic polynomial of this matrix, this is A, was this. And so that tells us that you have eigenvalues equal to 1 and minus 2. And the algebraic multiplicities are 1 and 2, because that's the number of times it appears as a factor of the characteristic polynomial. And then we also computed the eigenspaces. E1 was the span of this. And E minus 2 was the span of some two vectors. Let's call these V1, V2, and V3. So now in this example, the geometric multiplicity is the dimensions are what? The dimension of this is 1, and the dimension of this eigenspace is 2, which actually match the algebraic multiplicities. So if I go back to the sufficient condition that I stated in the last lecture, if the dimensions of the eigenspace are equal to the algebraic multiplicities, then you have n linearly independent eigenvectors. I mean, we could have just eyeballed that, right? We have these are distinct eigenvalues, and if the union of these has to be linearly independent by that theorem from the last lecture. So V1, V2, V3, which I'll call B, is a basis of R3. So that's all stuff from their last lecture. Now, the new thing is I'm going to now express A in this basis, right? So what is the matrix of A, of multiplication by A in the B basis? Well, let's follow our nose, right? So we derived a formula for this. Well, you compute A of V1 and write this in the B basis. Then you compute A of V2 and write this in the B basis. A of V3, write this in the B basis. That's just the matrix of a linear transformation in a basis. And now the punchline is that these are eigenvectors. So this is very straightforward, right? What's A times V1?
Is it just V1 because the eigenvalue is 1?
Exactly, it's just 1 times V1. Yeah. What's A times V2?
-2.
Negative 2 times V2. And negative 2 times V3. Okay, but now what are the coordinates of these vectors in the B basis? Let's see. How do you express V1 as a linear combination of V1, V2, and V3?
1, 0, 0.
Yeah, 1, 0, 0, right? 1 V1 plus 0 V2 plus 1 plus 0 V3. So actually the first column is just 1, 0, 0. Similarly, the second column is just 0, minus 2, 0. Third column is 0, 0, minus 2. And that's a diagonal matrix. So that's sort of the whole point, that if you have a basis of eigenvectors and you express the linear transformation in that basis, you always get a diagonal matrix. And algebraically, this is equal to P inverse AP for P having these vectors as columns. So this process is called diagonalization, and the whole point of doing this is that this D is now very simple, right? The coordinates don't interact. They're like this example on the bottom of this page. I turned something complicated into something simple.
Wait, could you say how you got the I understood everything until you actually wrote down the diagonal matrix.
Okay, yeah. So this matrix, the columns are the coordinates of 1 times v1 in the B basis. So that's 1, 0, 0 times 1, right? Similarly, the coordinates of minus 2 v2 in the B basis are 0 v1 minus 2 v2 plus 0 v3. And then minus 2 v3 when you write it as a linear combination of v1, v2, and v3 is 0 v1 plus 0 v2 minus 2 v3. So what would the coordinate vectors be? Well, there'd be 1, 0, 0, 0, minus 2, 0, minus 2, 0, and 0, 0, minus 2.
Okay, I was thinking that they were going to be the actual vectors, but this is the coordinate matrix.
Exactly. It's very important that they're the coordinate vectors. They're not the actual vectors, right? They're the coordinate vectors with respect to the B basis, which is the eigenbasis. That's why you end up with such simple coordinate vectors. Any other question?
What if like we can't find 3 vectors to form a base? Like what if we don't met the supplemental condition?
Then you cannot do this. You cannot always do this. This is well, you can't always do this, but you can do this a lot of the time, which is why it's useful. But it's a good question. You cannot always do this. You need a basis of eigenvectors.
And also, where do the similarity plays a part in this process?
Well, it played a part because, what did I actually do here? I found a matrix of A in the B basis, right? Here. But by what but remember when we talked about similarity, we said, what does similarity mean? Well, it's the same as finding the matrix of multiplication by A in some other basis. Right? TA in the B basis is the same as A times some change of coordinates matrices, which those are the P inverse AP.
Okay.
Right. So if I literally write this in terms of change of coordinates matrices, then that would be as P inverse AP for P being the matrix with these eigenvectors as its columns.
Okay. Okay. Thank you.
So I'll summarize this in general, since this is a very important thing. Maybe one of the top 3 things in the course, I would say. So here's a general theorem. An n by n matrix A is diagonalizable if and only if A has a basis of n linearly independent eigenvectors. So these two things are actually equivalent. I defined diagonalizability as being similar to diagonal. That's the same as having n linearly independent eigenvectors. Let me tell you the proof. Well, let's start actually with the second statement. So let's suppose A has n linearly independent eigenvectors. That's what it means to have n linearly independent eigenvectors. I'm just going to write that in matrix notation. So I'm going to form two matrices out of these eigenvectors. Okay. So I'm going to let P be the matrix containing these eigenvectors as columns. And let D be the diagonal matrix containing the eigenvalues. So now I can write all of these equations as a single matrix equation. What is that? Well, A times P is equal to A times this matrix, right? But now by matrix vector multiplication, that's just AV1 all the way to AVN. But then by the eigenvalue property, that's just lambda 1 V1 times lambda n Vn. Any questions so far? Let me clear up this A. So this is where I use the eigenvector equation, right? But now, okay, this is something you may not be familiar with, but you can verify it. This is literally equal to P times D. So maybe I'll write out the matrices. This is equal to V1 to Vn times this diagonal matrix. You can just check that. And then that's just equal to P times D. So I wanted to prove that A is similar to D. I didn't quite get that. I got AP equals PD. And D is diagonal, right? Anybody know what to do to get the similarity statement?
Couldn't we multiply both sides by P inverse?
Yeah, just multiply both sides by P inverse. You get P inverse AP equals D. So that's the proof. And the proof tells you what the similarity is. The P in the similarity is the matrix of eigenvectors, and the D is the matrix of containing the eigenvalues. Right? So the proof actually tells us a consequence. A is similar to not just any old D, it's the D it's similar to contains the eigenvalues. And this is why I said that the eigenvalues really capture the meaning of the matrix, right? Like change of basis means you just, I mean, at a high level, it's saying you change your perspective on the linear transformation. And what this is saying is if you have a basis of eigenvectors, if you view the linear transformation from that perspective, it becomes diagonal. And the numbers in that diagonal matrix are the eigenvalues. And that's why they're so important. So this is the general theorem that being diagonalizable is equivalent to having linearly independent eigenvectors. And we're not saying every matrix is diagonalizable. Okay, there are matrices that are not diagonalizable. We're just saying if it's diagonalizable, then that's the same as having n linearly independent eigenvectors.
Can we trust that P is always invertible?
Yeah, good question. Why is P invertible?
I mean, the vectors that make it are linearly independent, but
Exactly, yeah.
okay.
Yeah, so if you didn't have linearly independent vectors, you wouldn't be able to do the last step. and this wouldn't work. So that's the general theorem concerning diagonalizability. And I want to make some important remarks or remark. Not all matrices are diagonalizable. The simplest example, which is a good example to keep in mind for any kind of questions related to diagonalizability, is this matrix. So now the eigenvalues, or the characteristic polynomial, let's call this matrix J, is just t squared. So the eigenvalues are just 0 with algebraic multiplicity equal to 2. But there's only the dimension of the null space. So j minus 0 times I is just 1. So you only have one eigenvector. Don't have enough eigenvectors. So not all matrices are diagonalizable. But most, okay, in pure math, you often see matrices that are not diagonalizable. In the sciences, almost every matrix you see is diagonalizable. Okay, so in some sense, this is because, I personally never encountered a non-diagonalizable matrix until a few years ago, but that's a function of the area of math that I work in. But if you work in pure math, then this can be an important concern, diagonalizability. So just to see that we understand what's going on here, let me ask you a question. What's the relationship between diagonalizability versus invertibility? Can anybody tell me any relationship between these things? Or can anyone express both of these concepts in terms of, let's say, statements about the eigenvalues or eigenvectors? So can anybody see a relation between these?
Is it that a diagonalizable matrix, or sorry, that an invertible matrix is going to be diagonalizable?
Okay, so the question is, does invertibility imply diagonalizability? It's a good thought, but actually it doesn't. So, okay, I'll leave it as an exercise for you to come up with an example. And hint, it's related to this J matrix. So invertibility does not imply diagonalizability. What about the other implication? Does the diagonalizability imply invertibility? You can cast your votes in the chat. Some people are saying yes. A lot of people are saying yes. Answer is no. Because the zero matrix is diagonalizable, right? But that's not invertible. It's already diagonal. Any diagonal matrix is invertible. So there's actually no relation between these concepts, which I want to emphasize since there are so many relations in this course. And the way to understand why is diagonalizability is related to eigenvectors, right? If and only if A has n linearly independent eigenvectors, that's the theorem. Invertibility has nothing to do with the eigenvectors. It has to do with the eigenvalues. Now, can you tell me what invertibility means in terms of eigenvalues?
Wouldn't they all have
to be non-zero?
Yeah, A is invertible if and only if all eigenvalues are non-zero. I mean, the reason for that is, right, I mean, if AX equals lambda X for lambda equals 0, then you have a vector in the null space. A non-trivial vector in the null space. So there's no relation between these concepts. Diagonalizability is a question about eigenvectors. Invertibility is a question about eigenvalues. Okay, so no relation. Okay, here's an interesting remark which somebody mentioned in the chat. Well, if A is similar to D, right? Then, and the diagonal entries of D are the eigenvalues, then the determinant of A is equal to the determinant of P inverse times the determinant of D times determinant of P. But again, these cancel, right? So this is equal to the product of the eigenvalues. If, okay, well, we haven't said what happens if there are less than n eigenvalues. We'll talk about that next week. But this is another way to see it, right? If one of the eigenvalues is 0, then the determinant is 0, and that's if and only if. So this is how this relates to previous concepts that we learned. Okay, so now I want to show you an application. We're going to do another more serious application in the next lecture, but I'll show you why this is so important. I don't think it's a stretch to say that a large fraction of physics is dedicated to computing eigenvectors and diagonalizing matrices, and probably a pretty large fraction of math as well. Certainly, it's a very large fraction of what I am doing. But let me show you a very sort of down-to-earth application of this and why this is useful. So the application is to something which is called a dynamical system. In particular, this is something that's called a population model. So I'll show you, consider the following scenario. So suppose that, we have some population and we measure some feature of that population every year. So suppose, we have years n equals 0, 1, 2, 3, etc., etc. And suppose for some reason we're interested in what is happening at ski resorts in Lake Tahoe. So we let B of n be the number of snowboarders at Lake Tahoe in year n, and we let S of n be the number of skiers. And now, suppose we know at year 0, we know what the populations are. So in year 0, which is, let's say now, let's say there are 30 snowboarders and 10 skiers. Those numbers are kind of small, but okay. And now the interesting thing is every year these populations change according to some rules that might be kind of complicated. So you have an update rule. So the change that tells you the change in population from year n to year n plus 1. So I'm going to say that the number of boarders in year n plus 1 is equal to, goes up by 2, except, I don't know, you lose however many skiers there are. Not sure why. I mean, maybe I don't know. Skiers don't seem to like borders because they mess up the snow. But anyway, let's say they get rid of them somehow. And then the number of skiers in your n plus 1 is just goes down by half because I guess it's, well, I don't know. It was getting less popular at some point, but I mean, okay, you can probably tell that I'm biased in this case, but anyway. And then let's say, half of the snow borders actually become skiers. Okay, so this is a very general type of model. Yeah, okay, you can see there are some skiers in the chat. I don't think we're annoying on the chairlift, but anyway. So, so let's say you have some rule like this, okay? These are used to study all kinds of things. Animal populations like virus growth and things like this have been very relevant in COVID also. So the point is that there's some interaction between these numbers, right? And the question I want to ask two questions. Question one is, what is the total population after 10 years? And the second question is, what is the ratio of boarders to skiers? So this is a very general kind of question that comes up a lot. You want to predict the evolution of a population subject to some update rules. This is sometimes called population. I guess this is called a population growth model. It's a particular type. Okay, so, well, okay. First, let's write this in. So this is not so clear how to answer this, right? There's some interaction between boarders and skiers. And, the numbers are going up and down. If you plot this for a few years, it's not super clear. For just the first 2 or 3 years, it's not so clear what the pattern is. So the first idea is to encode this as a vector. Encode as matrix vector products. So what am I going to do? I'm going to let x naught be the state at time 0. And then xn is going to be a vector that's whatever the state is at time n. Don't know what that is yet. But then the update rule is given here. And there are some linear equations here, right? And the point is I can write that in matrix vector notation. So I can write that as Pn plus 1, Sn plus 1. So this is in general a useful thing to do. If you have a bunch of equations, write them in matrix notation. This equals the matrix 2 minus 1 half times Pn Sn. But then this is just xn plus 1. And this is just A times xn, where this matrix I'm going to call A. It's a 2 by 2 matrix. And so now to answer these questions, I really just need to compute a to the 10 times x naught. Okay, so that sounds kind of annoying, right? Because I have to multiply matrix 10 times. And the point is I'm now going to show you how to solve this very quickly using diagonalization. Okay. So step 1, compute eigenvalues. Compute eigenvalues and eigenvectors. And in this case, I'll spare you the computation since the time is running out, but we just follow the algorithm, right? Compute, do the characteristic polynomial, et cetera, et cetera. And you get that the eigenvalues are, in this case, 1 and, or I guess 3 halves and 1. And the eigenvectors are, or let me just write it this way. So A times V1 equals, or okay, let me just write the eigenvectors. The eigenvectors are 2, 1. So, and 1, 1. And okay, let me give these names. So this is lambda 1, and this is lambda 2. Okay, so I won't repeat the algorithm, but you can check that these are indeed eigenvalues and eigenvectors. And now step 2 is to diagonalize. So I know that P inverse AP is equal to just these diagonal matrix of eigenvalues for P being the matrix of eigenvectors. So 2, 1, 1, 1. So this, just follows from this theorem, right? If it's diagonalizable, then it's similar to the diagonal matrix containing the eigenvalues. So let's call this matrix D. And now the punchline is that once you have this, you can compute powers very easily because it's very easy to compute powers of a diagonal matrix. So step 3 is you have a to the 10 x naught equals PDP inverse to the 10 times x naught. So that's PDP inverse, PDP inverse, PDP inverse. But now these P inverse P's are just identity, right? So they all actually cancel and you get PD to the 10, P inverse, sorry, x naught. X naught. And that's something you can compute, right? So first let's compute P inverse x naught. So x naught was this vector 30, 10. P was this matrix 2, 1, 1, 1. I'll spare you the details, but P inverse x naught turns out to be 20 and minus 10. So that just means x naught is equal to 20 times V1 minus 10 times V2, right? But now we're familiar with this, just expressing x naught in the basis of eigenvectors. So we've computed this, and now we have that this is equal to P times, now this is the point, D to the 10 is very easy to compute. You just raise these numbers to the 10 times this 20 minus 10. And P was just a matrix with columns V1 and V2, right? And so now if you just write this down, you get that this is 3 halves to the 10 times 20 times the vector 2, 1 minus 10 times 1 to the 10 times the vector 1, 1. And that's the answer. But without even writing it out, I can tell a lot of interesting things about this, right? This term is blowing up exponentially. This term is going to be huge. 3 halves to the 10 is some large number. This is just staying at 1, right? So this term is, well, is small. And this is growing exponentially. So after a long time, this is going to be about dominated by the first term. And that allows me to answer question 1 and question 2. Question 1 is, what is the population about? Well, it's about the sum of these numbers, right? So it's about 3 halves to the 10, times 20 times 3. And answer 2 is, what's the ratio? Well, it's basically 2 is to 1 in the limit. Okay, so this is computing the eigenvalues and eigenvectors allows you to turn a complicated process like this one, in which everything is interacting into a simple process where you have quantities that do not interact. And I'll talk more about this in the next lecture, but basically the punchline is that the diagonalization allows you to understand long-term behavior of dynamical systems. Okay, and I'm over time, so I'll stop there.